Something changed on October 29, 2025. In the silent darkness surrounding our sun, an ancient traveler from interstellar space arrived at the point of closest approach, perihelion. But this was not a normal visitor. This was not a familiar comet from the Kuiper Belt or a frozen wanderer from our Oort cloud. This was 3Atlas, a cosmic relic estimated to be 7 to 12 billion years old, older than Earth, older than our sun, older than our entire solar system. It had been traveling through the emptiness between stars long before our world even existed. It had witnessed the birth and death of ancient galaxies, endured the radiation storms of the early universe, and carried within it the memory of a time when the Milky Way looked nothing like it does today. And then, at perihelion, something happened. 3Atlas began to brighten, as comets do when heat from the sun causes ice to vaporize. But instead of gradually increasing, its brightness suddenly surged at twice the expected rate, twice as fast, twice as bright, as though some internal switch had been flipped. Astronomers Kai-Cheng Zhang of Lell Observatory and Carl Battams from the U.S. Naval Research Laboratory were observing it in real time, watching through coronagraph instruments. They saw the explosion of light unfold across their data screens, yet they had no explanation. Their careful models, based on decades of comet physics, failed to predict this eruption. Brightness curves had been plotted, thermal analysis had been calculated, but 3Atlas did not follow the script. It was behaving differently. The timing was wrong, the rate of change was wrong. The comet was not just reacting to solar energy, it was responding in a way that seemed triggered, activated, as though something inside it had been dormant for billions of years, waiting for this moment. The influx of light was not soft and comet-like, it was abrupt, violent, intelligent, and within hours, the light signature from 3Atlas began to spread, forming an elongated glow unlike standard comet activity. No dust tail was visible. There was no glittering sparkle of ordinary comet debris, just a stretched, glowing presence, almost still, almost alert, almost watching. Scientists fell silent. This was no ordinary interstellar comet. It did not behave like Borisov or Oumuamua. It followed no known model. It was ancient. It was quiet. It was deliberate. And as it reached perihelion, something changed, something scientists didn't expect, something they still don't fully understand. For the first time, astronomers began asking questions they never imagined asking. What do you call an object that traveled billions of years through the void, only to reveal something new, something hidden, something timed, precisely at the moment of its closest encounter with the sun? What do you call something that doesn't follow the rules of comets? Would you still call it a comet? Or would you call it something else entirely? In the weeks leading up to perihelion, astronomers watched 3Atlas with increasing curiosity, noting a gradual rise in activity. But then something astonishing happened. In just 30 days, radiative observations confirmed that the object's water outgassing had increased not by 2 times, not by 10 times, but by 40 times. 40 times more water was being expelled into space than it had released just a month earlier. It was as though the comet had gone from a slow leak to a raging fire hose, blasting material into the solar wind with unexplained force. One scientist described it as a fire hose in space, spraying ice and vapor with the intensity of a high-pressure industrial jet, but even that analogy failed to capture the scale. Spectral readings confirmed the presence of carbon molecules, specifically C2, and imidazine compounds, NH2, classic signatures of ice sublimation. Under normal circumstances, these would be expected from a sun-warmed comet, but the problem was not their presence, it was their behavior. The release pattern was not gradual, as seen in typical comets, where heating slowly unlocks layers of frozen gas. Instead, it was exponential, sudden, and aggressive, like a switch being flipped. The data did not show smooth curves, but steep, abrupt spikes, as though the object had activated rather than reacted. And that raised a question scientists struggled to answer. If 3Atlas was expelling so much water and carbon-based gas, why was there still no dust tail? Comets, especially when heated, shed granular material, tiny rock fragments, mineral particles, ice crystals that reflect sunlight and create the spectacular dust tails we are familiar with. But 3Atlas did none of that. The brightness increased dramatically, the water vapor surged, but still no dust. Instead, telescopes captured only a stretched glowing presence, faintly elongated yet strangely uniform. No streaking, no trail, no debris. It was emitting but not shedding, glowing but not fragmenting. This was confusing. A comet under this much heating and releasing this much energy should be disintegrating, or at minimum producing granular dust. But 3Atlas remained visually intact, radiating rather than crumbling. It looked comet-like, but did not behave like a comet. Carl Bathams, who has observed hundreds of sun-grazing comets through SOHO's coronagraphs, said the activity defied timing expectations. "It's behaving as if it was triggered," he noted in a private analysis session. "It's like someone turned it on." His words were not implying artificiality, only that the activation appeared synchronized with perihelion in a way that natural comet physics rarely produce. Think of it this way: in nature, activity increases smoothly with temperature. The closer to the sun, the more gradual the rise, but 3 Atlas didn't follow that curve. Instead, it held steady, then erupted. Something inside burst free exactly when solar conditions crossed an invisible threshold. It did not awaken gradually. It awakened critically. And despite all the brightening, despite the violent release of gas, it remained strangely clean. No dust, no tail, only a stretched, glowing cloak around an object that still guarded its secrets. The images captured by SOHO, SWRI, and the newly commissioned GOES-19 coronagraph were expected to show something familiar: a glowing nucleus with a trailing dust tail stretching into solar wind, the classic signature of a sun-activated comet. But that is not what appeared on those screens. Instead, astronomers saw something different, something unfamiliar, something unsettlingly clean. There was light, yes, and lots of it. The object was radiating intensely after its perihelion brightening, forming a faint but noticeable glow. But there was no dusty tail, no granular scattering, no streaking patterns. Instead, 3 Atlas appeared as a stretched luminous form, elongated like a faint smear of light rather than a trail of debris. It was glowing but not shedding. It looked active but not eroding. It was behaving as if it was burning, yet keeping all of its structure intact. That was the first true sign that something was off. In comet science, dust formation is not optional. It is fundamental. When a comet approaches the sun, thermal stress cracks the surface, releasing ice and dust. The ice sublimates into vapor, while the rocky and mineral fragments form the dust tail, reflecting sunlight like a soft spray of glitter across space. The dust tail is not just a visual feature. It is the comet's identity. A comet without dust is like a storm with no wind, a volcano with no ash. Something essential is missing. So why was 3 Atlas producing massive levels of gas, but no dust at all? A leading theory proposed that a carbon dioxide gas layer had previously formed on the surface, acting as a temporary cooling shield. This layer, formed from centuries of CO2 freezing and sublimating in interstellar space, may have prevented traditional cometary activity as the comet first approached the sun. The CO2 would escape first, delaying the exposure of the deeper water ice layers and slowing the release of dust. Then, once the CO2 was depleted, the shield would drop, suddenly exposing the subsurface ice, causing a violent surge of water vapor and explaining the massive brightening observed at perihelion. It was a plausible explanation. It described how the sudden activation occurred. But it did not explain the shape. It did not explain the absence of dust. It did not explain why the object remained visually clean, with only smooth gas emissions and no granular scattering. And most importantly, it did not explain the timing. Dust behavior is controlled by granular structure and composition, but even if dust was scarce, some form of particulate debris should have appeared. There should have been some signature, some glittering trace, some fragment trail. But the comet remained strangely pure. Like something shedding light without shedding pieces, like something expelling gas but preserving structure, the coronagraphs did not show a dusty comet tail drifting away. They showed a glowing object holding itself together. And for the first time, scientists began to wonder, not just what 3 Atlas was made of, but what was holding it together. The James Webb Space Telescope was pointed at 3 Atlas months before its perihelion event, not to chase spectacle, but to quietly analyze its chemistry, its fingerprints. Using its near-infrared spectrograph, Webb dissected the light bouncing off the comet, searching for molecular signatures that could reveal its composition and origin. What it found changed the way scientists now look at interstellar objects. 3 Atlas was not what it appeared to be. The data revealed that its outer layer, its surface, was not pristine. It was not untouched material from another star system, preserved from its birth billions of years ago. Instead, it had been fundum. Entirely transformed by billions of years of exposure to cosmic rays, high-energy particles that roam interstellar space, bombarding anything they encounter. Webb's analysis showed that these cosmic rays had penetrated up to 50 to 65 feet into the comet's surface, changing not just the structure, but even the chemistry of the material. Carbon monoxide, which is common in young comets, had been transformed over time into carbon dioxide, indicating a long, ancient exposure to radiation. The ice had recrystallized into a new structure, harder, denser, and chemically altered. Bonds had been broken and reformed countless times until the material was no longer original. The outer shell was no longer simply ice and dust. It had become something else. Scientists now refer to it as an irradiated crust, a thick altered shell created not by design but by time and radiation. It was not evidence of where the comet came from, but evidence of where it had been. 3 Atlas was no longer just a sample from a distant solar system. It had become a product of its journey, a traveler shaped by the road, not the birthplace. But this raised a deeper question. If the outer layers had been modified, then what lay beneath them? Because Webb's data also revealed something important. While the surface had been transformed up to around 60 feet deep, the interior likely remained untouched, shielded by the irradiated crust. Beneath that modified shell could be a perfectly preserved core, material that has never been heated, never been altered, never been exposed to cosmic rays, material that still carries the original chemical signature of the ancient system it came from. That makes 3 Atlas not just a comet, but a vault. A vault carrying ancient, unmodified matter from before our solar system was born, matter that may have formed around a star that no longer exists, matter from a time before planets like Earth, before our sun, before life. But Webb's discovery also raised another possibility, one that scientists are careful not to claim, but careful not to ignore. If something lies beneath that shell, something preserved, something protected, is it simply ancient ice? Or is it something else? There is a long-standing problem in planetary science known as the meter-size collision barrier. Computer simulations suggest that when dust and rock fragments in a young solar system begin to grow, they can easily form objects up to a meter in size. But beyond that, they don't stick together. They collide and shatter. The environment of a protoplanetary disk is too chaotic, too violent, too unstable. So how do planets grow? How do they skip from meter-sized rubble to fully formed planetary cores? This question puzzled theorists for decades, until a new idea emerged. Susan Falsner, a computational astrophysicist from Germany, proposed a theory that changed everything. Her simulations suggest that young solar systems do not start from scratch. Instead, they may capture objects that are already large, objects that were born elsewhere, shaped in interstellar space, traveling through the galaxy for millions or billions of years. These objects, hundreds of meters or even kilometers in size, become ready-made planetary seeds. They bypass the meter-size barrier completely. They allow planet formation to begin not from dust, but from something already large, cohesive, and structurally stable. This idea solves multiple problems at once. It explains how planetary cores form quickly, even within the short lifetimes of protoplanetary disks. It explains why gas giants like Jupiter and Saturn seem to form faster around stars more massive than our Sun. It explains how some planets acquire unusual chemical signatures that do not match the rest of their solar systems. And most importantly, it explains why objects like 3 Atlas exist at all. Because 3 Atlas is exactly the size Falsner's simulations described, large enough to act as a gravitational nucleus, structurally cohesive enough to remain intact, radiation-hardened with its outer crust strengthened by billions of years of cosmic bombardment. It is ancient enough to have been present during the era of first-generation star systems. It could have participated in planet formation or narrowly escaped it. In other words, 3 Atlas may not just be a traveler. It may be unfinished, a planet that never formed, a building block that drifted instead of staying, a seed waiting for a home. If Susan Falsner is correct, then interstellar space may not be empty. It may be filled with thousands, millions, maybe billions of seeds like this, cores that never became planets, drifting between solar systems, waiting to be captured, waiting to grow into worlds. That raises a deeper question. If these planetary seeds form naturally, but survive only through certain conditions, shielding, structure, stabilization, then their existence is a result of cosmic engineering performed by nature itself. But if some show patterns that are too organized, too resilient, too timed, too purposeful, then we must consider another question. Are objects like this simply shaped by physics? Or were they shaped by intention? When scientists first estimated the mass of 3 Atlas, the number seemed almost too large to belong to a comet. Early models suggest it weighs approximately 33 billion tons, making it heavier than even Halley's Comet, one of the largest and most iconic comets ever recorded. Yet despite its mass, 3 Atlas has remained structurally intact through intense heating near the Sun, violent space radiation, micrometeoroid collisions, and forces that should have fractured it long ago. Its intact form raises an important question. How did something so old, so massive, and so exposed to space for so long remained so remarkably preserved. Its velocity adds another layer to the puzzle. 3 Atlas travels at nearly 130,000 mph relative to our solar system. That is fast enough to escape gravitational influence, fast enough to roam freely between star systems, and fast enough to resist being captured by any single sun unless by extraordinary chance. But it's not just the speed that matters, it's the path. Its trajectory is unusually flat, almost perfectly linear, cutting through our solar system like a straight arrow shot from deep space. It is too stable to be a random wanderer, too directional to be a fragment thrown out from a collapsing system. Its motion is consistent with something that has been traveling for billions of years with minimal interference. Then comes the age. Its estimated age of 7 to 12 billion years makes it older than Earth, older than our Sun, possibly older than our entire solar system by nearly 3 billion years. That means it did not originate here. It formed in a different solar system, under different chemical conditions, in a different era of the galaxy. It has been traveling through interstellar space since before Earth formed oceans, before the Moon existed, before our Sun began to shine. It has survived gravitational slingshots around distant stars, radiation exposure from supernovae, shockwaves from stellar winds, plasma storms, and collisions with micrometeorites across eons. So how has it survived? The answer may lie in its surface. The irradiated crust detected by the James Webb Telescope is more than just chemical residue. It is armor. Billions of years of cosmic ray bombardment did not destroy it, it strengthened it. The shell that now surrounds 3 Atlas is harder than ordinary ice, chemically altered into a crystallized, radiation-hardened casing. It acts like natural shielding, protecting the interior from further erosion. It is a passive survival mechanism, forged not through design, but through time and exposure. The longer it traveled, the stronger it became. And that brings us to the engineering question. Is 3 Atlas merely a survivor, or something designed, shaped, or reinforced by its environment in a way that mimics engineering? It behaves like an object built to endure, built to travel, built to protect whatever lies inside. But the most unsettling part, we don't yet know whether it became that way naturally or intentionally. At first glance, 3 Atlas behaves like a comet. It gets brighter as it approaches the sun. It releases gas. It glows in ultraviolet light. But when scientists looked closer, the pattern didn't match ordinary comet activity. A normal comet responds gradually to solar heating. Its sublimation increases smoothly, following a predictable temperature curve. But 3 Atlas did something different. It remained relatively stable, then suddenly activated exactly at perihelion, almost as if triggered. The transition was not gradual. It was threshold-based, like something waiting for a specific condition before releasing its energy. This is not a typical comet response. This is activation. So scientists ask the question quietly, almost reluctantly, could this be passive, or could it be programmed? Today, we already build space probes that remain dormant for years, even decades, only activating when they receive sunlight or heat signals. We place hibernation systems on deep space probes that wake up when their solar panels detect enough energy. These designs are not advanced speculation. They are basic engineering. A dormant system triggered by proximity to a star is something humans already understand how to build. That does not mean 3 Atlas is artificial, but it does mean that its behavior, activation rather than sublimation, resembles the logic of a design system more than the randomness of nature. Scientists are careful with their words. They are not claiming intelligence. They are simply noting that the phenomenon appears conditional, responsive, and timed. And then comes the challenge. Even if something were designed, how would we know? We have tools to detect natural compositions. We can classify molecules, measure radiation, track trajectories, but we do not yet have a scientific framework to detect artificiality in a natural-looking object. We do not know what to measure. We do not know what patterns to look for. And perhaps most importantly, we do not know what questions to ask. What would count as evidence? Intentional symmetry, material not explainable by natural formation, energy emissions that follow coded rather than random patterns, non-gravitational accelerations that do not match any known sublimation model. The truth is we don't know, because in all of recorded history, we have never confirmed an artificial interstellar object. We have no baseline, no classification, no comparison model. So when scientists observe behavior like threshold activation, they do something not often seen in research. They pause, they hesitate, they leave space for the unknown. Avi Loeb, former chair of Harvard's astronomy department, said it best. Uncomfortable doesn't mean unscientific. He argues that science should not dismiss possibilities simply because they feel unlikely. He believes that when objects behave in ways we cannot explain, we must expand the questions, not shrink the data. Maybe 3 Atlas is entirely natural, a cosmic survivor shaped only by physics. Or maybe it is something we are not yet equipped to recognize. When 3 Atlas began showing signs of unusual behavior, the scientific community responded with caution, analysis, and quiet curiosity. But one voice called for something different: full transparency. Professor Avi Loeb, former chair of Harvard's Astronomy Department, made a formal request for NASA to release the complete datasets gathered from all instruments observing 3 Atlas, including raw spectroscopic data, plasma interactions, trajectory modeling, and radiative emissions. His goal was not to prove it was anything artificial. His argument was simpler, more fundamental. He wanted to ensure that every possible explanation was considered and that no data was withheld from independent scientific review. For Loeb, this was not just about 3 Atlas. He reminded the community that our 2 previous interstellar visitors, Oumuamua in 2017 and Borisov in 2019, also showed anomalies that cannot be easily explained using conventional comet models. Oumuamua accelerated without a detectable outgassing tail. Borisov behaved more like a hyperactive comet with composition unlike any seen in our solar system. Loeb argued that when 3 interstellar objects arrive, and all 3 display unexpected behavior, we should not rush to dismiss the anomalies just because they make us uncomfortable. He stressed that science is not about protecting assumptions, it is about testing them. It is about letting data, no matter how strange, redirect our thinking when necessary. He warned against what he calls premature dismissal, the tendency to explain anomalies before fully examining them, simply because the alternatives feel speculative or controversial. In his own words, when data challenges our models, it is not the data that must change, it is the models. Loeb's concern is not that 3 Atlas must be artificial. His concern is that our current scientific approach might fail to detect opportunity. He believes that unusual patterns, perhaps something subtle, something buried, might exist within the high-resolution spectroscopic or plasma interaction data. Patterns that could reveal something profound, not necessarily artificial, but something about interstellar chemistry, early planetary formation, or even unknown classes of objects that do not exist in our solar system. But if the raw data is only analyzed by a small group of mission scientists, he argues, we risk missing alternate interpretations. Thousands of researchers worldwide could analyze the same data using different tools, different models, different perspectives. That is how science grows, not by narrowing options, but by expanding them. He asks a critical question: are we investigating this object as it is, or only as we expect it to be? Are we labeling it a comet simply because comets are familiar? Are we interpreting its behavior using comet models because those are the only models we have? And if so, what might we be missing? Loeb does not say 3 Atlas is artificial. He simply warns that we do not have a framework for identifying something that isn't a comet, asteroid, or planet, but might still be natural, something shaped by time, radiation, or unknown cosmic processes, something unlike anything in our models. He believes the truth may be in the data, but we have to be willing to look for it. Right now, 3 Atlas is moving away from the sun, heading deeper into space again, fading, dimming, and slipping back toward the darkness it came from. But for a brief moment in these crucial weeks between November and December, it is still visible. This is the final observation window. Once it grows faint, once it crosses the observational limits of our instrument, it will be gone, possibly forever. No return, no second chance, no orbit. A one-time visit in the lifetime of our civilization. Every major observing facility is now pointed toward it. The James Webb Space Telescope has extended its observation schedule to capture post-perihelion infrared signatures. NASA's stereo satellites are analyzing plasma field interactions around the comet's coma. The Swift Ultraviolet Telescope is measuring hydroxyl emissions to track water vapor. Even the Mars rovers, Curiosity and Perseverance, were positioned to capture unique angles of observation from the Martian surface, giving scientists a stereoscopic advantage that Earth alone can't provide. This is no longer just observation, it is assessment. What scientists are trying to determine is simple. How does 3 Atlas behave now that the intense heat of the sun has passed? Does the brightness continue to rise, even with declining solar input? That would indicate internal activation, something within the nucleus reacting, not merely surface sublimation. Or does it begin to fade predictably, following the typical cooling curve of a natural comet? That would suggest it was behaving naturally all along, just more violently than expected. Telescopes are also watching for non-gravitational forces, tiny orbital corrections that may indicate focused outgassing jets. If gas release is uneven or directional, it could gently push the object off its predicted trajectory. If those shifts align with solar heating, then the behavior is natural. If they do not, if the trajectory changes when no external force is expected, that would be something different. Spectroscopic instruments are checking for chemical changes. When a comet's outer layers are stripped by solar heat, the inner material, if untouched, should become visible. Scientists are watching to see if new molecular signatures emerge, revealing untouched core material from a previous star system. If nothing changes, then the crust may go deeper than expected. If new compounds suddenly appear, we may be looking directly at the untouched material of a star that no longer exists. And then there is the hardest question of all. Is the outgassing random, or does it show patterned behavior? Comets do not pulse. They do not regulate. But if energy release happens in uniform bursts or shows periodic behavior, it would demand an explanation we do not currently have. Scientists are silent now, but intensely focused. No one is drawing conclusions. No one is claiming certainty. The next few weeks will decide how CometAtlas is remembered, either as a wildly unusual comet or something that doesn't fit comfortably into that category. Because it is leaving, fading, taking whatever secrets it carries with it into the darkness. And once it goes, it will not come back. In the end, science may classify CometAtlas as an irradiated interstellar comet, a rare but still natural object, shaped by time, radiation, and the harshness of deep space. Or it may be given a new category, something fundamentally undocumented, a type of cosmic relic we have never studied before. But even in the simplest interpretation, even if it is nothing more than an ancient survivor of a lost solar system, CometAtlas still changes something important. It expands our understanding of what exists between the stars. It reveals that interstellar space is not empty. It is alive with objects, stories, and matter older than our own world. It proves that space between stars is not a void, but a corridor of travelers, carriers of time, of chemistry, of history, seeds of planets that never formed, fragments of worlds that once were, remnants of stars that no longer exist. And if objects like this drift between stars, not in thousands but in billions, then we must ask, what else drifts among them? What else moves silently across the galaxy, rarely noticed, rarely understood, waiting for the moment when sunlight touches it again? CometAtlas forces us to ask a profound question for future explorers, scientists, and thinkers. Is the universe only natural, or also intentional? Are all cosmic structures merely byproducts of physics, or could some be shaped by purpose, by design, by will? Our instruments can detect matter. They can measure light. But can they detect intention? Can they measure purpose? Maybe CometAtlas is entirely natural. Maybe it is simply a comet that experienced an extremely long journey, hardened by time, awakened by sunlight, and now disappearing once again into the dark. But the true mystery may not be what it is, but what it might have been. A failed planet, a preserved archive, a dormant traveler, or something we do not yet have words to describe. Its greatest legacy is not its chemistry, not its brightness, not its missing dust tail. Its legacy is the questions it leaves behind. It arrives, behaves in ways we struggle to explain, and disappears. It comes not to give answers, but to force better questions. And perhaps that is the point. Some visitors do not come to be understood. They come to remind us to listen. Because the universe is speaking. The real question is, are we listening?